I will make the presentation afterward. So thank you. Please go ahead. Thank you, Javier.
Okay, thank you, Silvia, and thanks a lot for the invitation. So please feel free to stop me at any point, and if you have any questions, I will be talking about some our latest results that come from a run that we did during the lockdown. So during last spring, spring 2020, and this run was collected at Fermilab using a setup at the Minos underground facility that we have at Fermilab. So this was all in preparation for the deployment of the full system at SNOLAB, as I will talk about. Okay, so first I'm gonna present a very, very short history of the project. So the project started a little bit before 2017. This was an LDRD project within Fermilab. LDRD is laboratory-directed research and development funding that is usually done for high-risk, high-reward projects. And this was to move forward and build the first instrument using the Skipper CCD technology that at that point was pretty much abandoned. So in 2017, we had the first demonstration of this sub-electron noise, deep sub-electron noise, reaching 0.06 electrons RMS of noise and being well within the electron counting regime. So in 2017, 1 year after that, we had our first surface run for dark matter searches. This was done at Fermilab, and this allowed us already to explore some available parameter space for high cross-section dark matter and also for very light dark matter, even with a tiny prototype using these sensors that we fabricated. Then in 2019, we did the first search using one of these prototypes. It was the same prototype as the one that we used in 2018, but we took it at Minos facility that is 100 meters underground, and we had our first dark matter search underground in a relatively low radiation environment. And today I will present the results from the first run using a dedicated batch of sensors that we fabricated specifically and optimized for dark matter searches. And this is the search done using science-grade science CCDs. All the other CCDs that we used were R&D CCDs that we fabricated parasitically to reduce cost, because in 2016, when we started this project, we didn't have much money. And also I will discuss the next steps, that is the full-scale deployment of the experiment at SNOLAB. Okay, so first, a very brief summary of the SENSEI collaboration. We are a relatively small collaboration with 4 institutions. Most of the hardware R&D and fabrication is done at Fermilab, and a lot of the analysis is done by the other institutions. And now also the Tel Aviv University, with the addition of Sho Uemura, is starting and ramping up on the hardware side. So what's the idea behind our sensor? So what we are looking for is for interactions between dark matter particles and electrons in a CCD, in the crystal that is the silicon crystal that the CCDs are made of. So to be perfectly clear here, we are using the CCDs as targets themselves. We are not using the CCDs to record signals produced in another media, but to record interactions that happen within the CCD. So that's why we want to have sensors that are CCD sensors that are as massive as possible. And I will talk about that also later on. So what we are looking for is interactions between dark matter and the electrons in the crystals. We focus on the electrons as targets, although of course the dark matter in principle could also interact with the nuclei in the crystal. But because we are focusing on light candidates, we use the electrons as targets and in this way we are able to reach much smaller masses and explore areas of the parametric space that were previously not accessible. So in principle, the silicon band gap is roughly 1.2 eV, and that is the amount of energy that needs to be deposited to produce a ionization event of one electron. And that is, in principle, the theoretical threshold of our sensors. Another thing is that all these interactions, they happen within the scale of 1 pixel, because the track length of an electrons with EV scale energies is much smaller than the pixel size. So we are looking at events that are happening within 1 pixel and are essentially point-like. So I will now briefly discuss how CCDs work, because they are different from many other detectors that maybe you are more familiar. The way CCDs work is by collecting charge in 1 pixel and then shifting it 1 step at a time towards one of the what we call a serial register. So here, I'm going to slow down here a little bit because you might not be familiar with these things. What we are looking here on the right is a CCD seen from the top. In this case, it is split in 4 quadrants. So each quadrant essentially is like an independent CCD. So let's focus on this one, for example. Here we have the active area, that is this region here, that is a 4x4 pixel in this case. And if we have an interaction of a particle within this region, it will produce ionization, and the ionization will sit in one of these pixels. Then what we do is we wait and accumulate charge this way, and we can have the charge sitting there for hours or even days without anything wrong happening to it, anything bad happening to it. And then at some point we decide to read out, because what is very important is that none of these pixels in the sensitive area of the CCD is actually instrumented or connected to anything. So at some point we decide to read, and what we do is we shift the charge 1 step to the left here. Okay, so the charge that was in these pixels goes into this other structure that it's called the serial register. Then we keep all the charge here still in the active area, and then we start shifting the charge in the serial register by 1 pixel at a time towards the amplifier, that is the readout structure that I will discuss in a minute. So in this way, we read the charge in the full CCD 1 pixel at a time through all 4 of these quadrants that the CCD is made of. This is the way conventional CCDs work. There is nothing new here, so no skipper magic yet. I haven't described that. And this is how standard CCDs work, and they can reach a readout noise of about 2 electrons RMS. Okay. So if we focus into the readout stage, I will first talk about how a standard CCD works and then describe what is different in a skipper CCD. So in a standard CCD, what we do is that first we have this sense node structure that is essentially a capacitor this is connected to a voltmeter. Okay, so we first measure what is the voltage here when there is no charge in this capacitor, and we call that the pedestal. Then we shift the charge that has been accumulated in 1 pixel that is now in this structure that we call the summing well, that we have the freedom to move up and down by controlling the voltages there. And we move the charge into the sense node. And then, of course, because this capacitor is small, this changes somehow the amount of voltage that you sense on the other side of the capacitor, and that is what we call the signal. And the difference between these 2 voltage level is related to the amount of charge that you have there. So by integrating longer, you can in principle reduce the noise as much as you want. Okay, so on the left here is how a conventional CCD works. And what we have is that if you have a high frequency noise, by integrating for a longer period of time, okay, and measuring your voltage for a long period of time, you can average out all the high frequency noise in the pedestal and in the signal region. In principle, if you only had high frequency noise, you could reduce the noise as much as you wanted by integrating longer or by measuring longer each of these levels. The problem is that all the transistors that we know how to build have what it's called the 1/f noise, that is a low frequency noise that goes up very, very rapidly at low frequencies. So at some point, you start integrating these low frequencies, and that is the limitation of the standard CCDs. So you can reach, by doing this thing, about 2 electrons RMS of noise. On the skipper CCD, the situation is different because in this case, we are able to take multiple non-destructive measurements of the charge by moving it back and forth between the sense node and the summing well. And the good thing about this technique is that in principle, you can reduce the impact of the low frequency noise as much as you want. And at the same time, by taking many, many samples that are independent and non-correlated, you are able to also average out the high frequency noise. So in this case, you are able to pick at which frequency you want to measure, and in this way, reduce the impact of the low frequency noise. And by doing this, the skipper noise scales as 1 over the square root of the number of samples that you take, the independent samples that you take between this shift of pedestal and signal level that you are repeating at a relatively high frequency compared to a standard CCD. And what you see here is how this noise, how the spectrum looks like. So in the upper right part of this slide, you can see, for example, spectrum in which we are measuring the charge from pixels that are empty, and then you see 0 charge, then 1 electron. And also the beauty of this design is that the noise level, the RMS, is independent of the occupancy. So in principle, you have the same resolution even for very high occupancies, as you can see here. For example, you are perfectly able to discriminate between 776 and 777 electrons, and you have the same RMS. Then one drawback of this technique, of course, is that because you are taking many samples for each pixel, the readout time can be large. So in here, what you are seeing in the lower left plot is how this noise goes down as you increase the number of samples. And what is important is that this line is not a fit. We are just taking the noise for a single sample and dividing this by the square root of n. Okay, so you see that we are already in the theoretical limit, and there is only a very small difference once you reach the order of 4,000 samples. And the RMS for that is essentially 0.06 electrons RMS. In many cases, you don't want to go to those levels of noise because that's not required. You don't need to spend that amount of time reading out. But the nice thing about this is that you can change the number of samples that you take dynamically and decide what is the optimal between readout time and the noise that you are able to live with. Okay. So now our sensors, the ones that we use for SENSEI. Here is a picture of the sensors that after fabrication and dicing. This is a full wafer in which we have 6 sensors. We fabricated these things in ultra high resistivity silicon on a thick wafer that is 675 microns thick. So this is very different from the CCDs that are used for astronomical applications, that they go through a thinning process in which most of this mass is removed and they are only 100 or at least 200 microns thick. These were fabricated in Canada in a company that it's called DALSA, and were designed by the Steve Holland's group at Berkeley. This is the Microsystems Lab, and we have a long-standing collaboration with them that has produced many, many beautiful results. So they are really great. The first dedicated production for skipper CCDs optimized for dark matter was the sensors that we are using now for SENSEI. Essentially, each sensor is roughly 2 grams, up from 0.1 gram. That was our prototype sensor for proto-SENSEI, the first 2 results that I told you about at the beginning. And also, because we are using now high resistivity silicon, we improve the dark current by orders of magnitude. And I will talk about this also a little bit more. So after we get the sensors at Fermilab that we are fabricated at DALSA, we have to package them so we can actually connect them to our controller and readout electronics, and also cool them down and provide shielding from environmental radiation. So this here is how our packaged sensors look like. What you see is a copper module that contains one CCD here that is epoxied to a silicon substrate that is slightly thinner and longer. This is the piece that you see here. The CCD is this rectangle that is beneath this piece of silicon that is also made of the same high resistivity, low contamination silicon as the CCD. And then it has some metallization traces on top that are then wire bonded to a flex cable that you see on the right. This provides mechanical support and also electrical connection and interface with our outside electronics. And the copper module provides the thermal connection also through a leaf spring that you can see here on the bottom that presses on this silicon spacer that is all epoxied on top of the silicon support, the silicon circuit, and provides good thermal connection. Then that is connected to a readout electronics that was designed in-house that we call, this is the low threshold acquisition or LTA electronics. This was designed by Fermilab in collaboration with institutions in Latin America, in Argentina and Paraguay. And this is an extremely nice readout system that is very modular and scalable for our needs, because we will deploying several sensors at SNOLAB, and essentially each board can read out one sensor, and the design is extremely flexible for our application. Our previous readout electronics, you can see it on the lower left. It was very bulky and it looked more like a small fridge. And this has to be compared with a board that is a small and very, very manageable, and it provides a lot more flexibility than our previous system that we use in R&D. So we are very happy with this deployment. Then here is how our current setup, the one that it's running in Minos, looks like. So Minos is a shallow underground site that is about 100 meters underground in the Fermilab campus. We are sitting in the neutrino drift that just across the NOVA experiment. We have a cleanish tent in which we installed all our systems, and this is how it looks like on the right. So we have vacuum pump that is connected to a copper cylinder, and this copper cylinder is also connected to a cryo cooler. We use a cryomake that is a closed circuit system using a cryo refrigerator that runs on helium. It's the same one that we have at SNOLAB now. So you can see on top the LTA board, and then so inside this vessel is our sensor, and surrounding it we have this relatively low-tech shielding made of lead. This is how it looks like inside. So inside the vessel, what we have is essentially a cylinder that on top has some lead that isolates the sensors from the top electronics, that is the and supporting equipment where the cold head and other electric lines are. And then on the bottom part, we have the module that I showed you in a slide before. So we cooled this down to 135 Kelvin roughly. So this is relatively simple to achieve. This is well above liquid nitrogen temperature, so we are not talking about millikelvin refrigerators here. And we bias these sensors with a bias voltage of about 70 volts. Then this plug goes into this cylinder here, and then the LED bricks are surrounding the module that we have here. Okay, so the idea of this setup was not to provide the highest quality for scientific results, but to provide a test bed for all the sensors that we are deploying at SNOLAB. Regardless of that, the sensitivity was more than enough to produce very interesting results, as you will see. So our first data set, this was done with our first packaged sensor. You have here the 4 quadrants. One of the quadrants was not working. We were able to track this down to a bad wire bond. But regardless of that, we had 3 working quadrants, and we could use them to perform a dark matter search. So we had exposures that were taken over 20 hours. So all the charge was sitting there for 20 hours, and then we read out. Because these are slow sensors, as I mentioned before, the full readout took about 6 hours for the level of noise that we wanted to achieve. So overall, it took more than a day between each readout was completed. Then we selected 7 images, and we unblinded them and used those for developing our analysis. And then we kept a blinded data set of 22 images that we used to produce the results. Okay. So the overall mass of this search was about 28 gram days after we removed 1 quadrant and used these 22 images. Okay, so here I am just zooming into one of the images, just the sample images, so you can see how they look like. And what you can see is these straight lines, these things that look like comets. Those are muon tracks. And then you have these curvy and wavy lines. Those are electrons, high energy electrons that get scattered after each interaction and then just wiggle around. Then you also have these roundish events, okay? Those, like this one, small ones, those point-like events, those are coming mostly from X-rays. Some of them can be also electrons with less energy, and they do not have a track that it's long enough to produce these extended tracks. And you also see some kind of pepper around. So these are pixels with a small amount of charge, and we are able to detect, as I mentioned before, single electrons. So I will focus on those shortly. So in this search, we split our analysis into 2. We did what we call the single pixel search, in which we looked for events in which all the charge was contained in a single pixel and was not split into 2 or more pixels. And that has the best sensitivity for single electron events, and also that, of course, are always on a single pixel, but also for 2 electron events. And I will discuss this also in detail. Then for 3, 4, and more electrons, we also did a search. But in this case, we do a clustering and allowed for the events to have the charge split between several pixels that are neighboring. The reason for that is because the CCDs are very, very thick, and when you have an interaction in the bulk of the silicon, the electrons that are produced in that interaction, they drift apart while they travel up, and they are collected in in the front side of the CCD. And then even like they can be produced in exactly the same point, at the end, the charge can be split between 2 or more pixels that are neighboring. Okay, but this process is extremely well understood, and I will talk about this also in some detail. As this was the first search done in this energy range, we also started to look for other sources of backgrounds that were not known, and also compare the expectations with some known sources of background, like Compton events, low energy Comptons, and also spurious charge that we know that can be generated on the CCD, dark current that is just the thermal excitations of electrons that are below the band gap into the conduction band, and also look for other things, because this was the first time that this was done. So the first thing is that we do an identification of bad regions of the CCDs where defects might be present. So we do that by running the CCDs at a relatively high temperature where the dark current is greatly enhanced. And you can see here these lines, these vertical lines, those are regions in which we have a defect. And then even though when you cool them down, these defects become less and less important. After the identification in these high temperature runs, we just mask out these columns so they do not count in our analysis. Then another thing that we masked out is these lines that you see here. Those are what we call serial register hits. Because the readout takes a long time, there is a chance that a particle just interacts in where the serial register is, and that produces a line with a relatively large amount of charge that looks like this, but that can also split into a small charge package before and after it. So we are masking all the lines where we see a structure like this. Then another thing that is also a well-known problem in CCDs is what it's called the CTI, or charge transfer inefficiency. And you can see that as this kind of low energy clusters that are above, of these high energy tracks. This is because in these images we are reading out towards the serial register is downwards, so we are moving the charge in this direction, and sometimes you have some probability of leaving behind a tiny amount of charge. And if you have a trace that has thousands or millions of electrons in the pixels, sometimes you leave behind some charge, and that appears as clusters that we call bleeding, that is downstream of the movement of the charge during the readout. So we also mask the regions that are downstream of high energy events. Another thing that we observed, and this was observed for the first time, and this was extremely interesting as it also impacts other experiments that are being designed or trying to run in this low energy region, is that we observe that there is a halo of light of low energy events that surrounds the high energy events. So in this plot on the right, what I'm plotting is the rate of single electron events as a function of the distance towards a high energy cluster. And you can see that there is a very high excess when you are looking in the region that is nearby these high energy clusters, and this goes down as you get further and further away from this cluster. So these are low energy photons in the infrared range that can actually travel far away in silicon and then before they interact. And they are reconstructed as independent events, but they are surrounding the high energy events. This was the first time that something like this was identified. And there are now very interesting explanations for what's the main contribution to this. And what we think now is that this is coming from Cherenkov radiation. But I don't have time to discuss that in that level of detail. But this is also very interesting for other experiments looking in this mass energy region. Then in here, we were able to measure the single electron rate in our CCDs, and we can also compare that to the expectations that we have for dark current, and given the fabrication parameters of our CCDs and the measurements that we can take of the dark current at high temperatures. And what we observe is that the single electron rate, although it goes down as we reduce the temperature, it is higher, much higher than what is expected from the naive expectation that comes from dark current. And at higher temperatures, this really behaves as what the model predicts. I'm not showing that here, but this really behaves as the model for dark current predicts. But once you start getting to lower and lower temperatures, this deviates, and then it gets to a plateau that is roughly around this region. Okay, that is 140 here, or 145. We get to a plateau, and that plateau is not it does not keep reducing as we lower the temperature. Okay, what we expected here is that the dark current would be as in the solid line here, so it should be 1 order of magnitude smaller at 135, and we try to understand where this contribution is coming from. Okay. So the first question that we ask is if these events are increased with the amount of time that you expose. So what we have here on the top right is just the rate as a function of the time that we expose. And you can see that this goes up very nicely linearly, as you expect, but also that it has a non-zero start. So the intercept is non-zero, and that is something that you get regardless of the amount of time that you expose the CCD. So this is also a known source of charge in CCDs, that it's called spurious charge. That this is electrons that might be promoted into the conduction band just by moving up and down your voltages in the CCD when you are doing the shifting of the charge in the active area and the serial register of the CCD. But this is the first time that this contribution could be measured at this level. So what we have here is that there is an exposure-independent contribution that is roughly 1.5 electrons per pixel per readout. Every time we read out, we get this amount of pixels, this amount of charge. And then after correcting for this effect, on the right, you see that we went from the gray star here to the blue one. So it was reduced by a factor of 2, but we are still far away from our expectation from the dark current model. So this we studied further, and what we found, and this was also for the first time, that the amount of events, of single electron events, was reduced when we increased the amount of shielding around, so that there was a very strong correlation between the single electron events and the environmental radiation. And this was in principle not modeled in any of the background models that was existing before this. And we understand this as coming from a few different sources. Some of that is infrared photons that are produced in showering of the high energy tracks when they travel through silicon, and also the surrounding material of the CCDs. So we expect that this will scale as the environmental radiation. So we are really looking forward to our run at SNOLAB, in which we expect that this will be reduced by 100-fold. So yeah, but we saw a very clear correlation between the rate and the environmental radiation. So essentially here on the two plots on the bottom, you have on the right the high energy spectrum with and without the extra shield that we have, and then on the right the rate. So now these error bars of running without the shield have been greatly reduced. So they really scale like the amount of environmental radiation. So another cut that we introduced in our analysis was what we call the loose cluster cut. In this case, we look for clusters of events, even though they might not be neighboring pixels, just local excess of events, and we are able to correlate those to mini showers in the shielding or other similar events. And after applying those cuts, you see how the remaining effective area of the CCD looks like on the right. So this is after applying all of our cuts. So masking high energy events, the halo around them, the bleeding regions, the bad columns that are due to defects, and also these loose cluster cuts. So the black pixels are the ones that we end up using after all these quality and fiducialization cuts. So to show you what's the impact of these cuts, here I'm showing you the several spectra after applying some of the cuts in order. So without any cuts, you have this black and red spectra here. And then after applying all the cuts, you can see that we get the pink spectrum in which we only have a handful of 2 electron events, no 3 electron events or plus, and also the amount of single electron events is greatly reduced by more than an order of magnitude. Okay. So then we had to study the efficiency of all our cuts, and in particular for the 2 electron analysis, in which we had the single pixel requirement. And as I mentioned, we had to study this in detail to understand what was the probability of 2 electrons that are produced in the same position ending up in the same pixel. And we studied this with muon tracks and also with X-rays, and we were able to produce a very accurate model of this. And this was also based on our previous experience with CCDs working within the DAMIC experiment. And after this, we find out that the efficiency for our 2 electrons to stay in 1 pixel was roughly 23%. So that's the efficiency price that we are paying for requiring that the 2 electrons are in the same pixel. At the same time, we get a much smaller chance probability of 2 single electrons that are independent of producing a cluster. Okay. So after applying all these cuts, this is how our search looks like. For the 1 and 2 electron events, we have some, for our 1 electron and 2 electron channels, we have some events, but anyway, we can produce a limit. And also then for the 3 and 4 electron events, this is a background-free search, and we do not have any events in our unblinded data set. So this in the center, you can see our result for light dark matter with a light mediator, and we produced what is currently the world's best sensitivity in the full mass range. Then for heavy mediator, we have the best sensitivity between 10 and, well, below 10 MeV. And then we also produce exclusion plots for absorption channels in which the dark matter particle is fully absorbed in the crystal, and then the full mass is available, and then we have the best sensitivity below 10 eV in this case. So these are all extremely interesting results, and are, as far as I know, currently the world's best results in sensitivity, even from this very limited run, using a prototype sensor at a shallow underground site. So we expect to have a lot of improvement once we run at SNOLAB very soon. So what's the future of this technology? So there is SENSEI that is currently being deployed at SNOLAB. The sensitivity predictions for SENSEI here on the right are the green line here. And as you can see, it can explore all this shaded region that it's labeled as key milestones. This is where many of the models are most theoretically motivated. And also, this is for the heavy mediator, and then for the light mediator, there is this line that is the key milestone. This is a shaded region in which also the theoretical motivation is highest. So with SENSEI, you can see that we expect to go many orders of magnitude under this key milestone. So even at the very beginning, we might be able to start probing this region very quickly, and that would be extremely interesting. After that, there are two other experiments that are using the same technology that we developed. That is the DAMIC-M project that is aiming for the construction of a kilogram scale experiment, and then that is going to be in Europe. The time scale is a few years after SENSEI. And then there is the Oscura project that is aiming to build a 10 kilogram scale experiment, and the site is not yet decided, but we are in the R&D phase and for that project. So what's going on now? We are building the Fullscale SENSEI experiment that will be deployed at SNOLAB. We already have a phase 1 system running at SNOLAB that we use to produce very important information regarding how to optimize our package design and how we want to operate the sensor that is currently running underground. And here you have on the bottom left one of the pictures that was taken during the deployment of that phase 1 system. Then on the right, you have the picture of the full vessel that this was taken at Fermilab, where we did a full integration test during December 2020. So all the parts have been fabricated, tested, and validated. And after doing this testing at Fermilab, we shipped everything to SNOLAB. So all the things are currently at SNOLAB underground, and we are now going through the work readiness review. And after that is done, we hopefully will start building this vessel at SNOLAB. Well, actually, you will be building this vessel at SNOLAB, because I mean, this was also extremely important for the progress of the project, that SNOLAB really wanted to get involved and help us with this task. It's providing a lot of support for doing the first remote installation of an experiment at the lab. So we are extremely thankful for that, and thanks for all the support. Yeah, and I think that's it.
So thank you very much for the nice talk. Are there any questions? You can raise your hand in the chat with the, or you can just, okay, Fabrice.
Okay, sorry, I try not to be the first. So it's Fabrice from Triumph, actually, I'm not SNOLAB. I had, well, one thing before I ask my question is we are organizing the TIP conference, instrumentation in particle physics, and we would want to have a talk from SENSEI. So if you see an email from me or Sylvia, please reply.
Okay.
And then the other thing is, so I have two questions. One is you put 70 volt. Does that mean the CD is depleted, or is it undepleted?
No, it's fully depleted. Actually, our CCDs get fully depleted at 40 volts, even though they are very thick because they are super high resistivity. Already at 40 volts, they are fully depleted. But we increase the voltage to reduce the diffusion and have more chance of having all the charge in a single region.
Okay, great. If I can ask one more question. So when you do this sampling many times, so you go sample pedestal, sample signal, yes. Doesn't this switching introduce noise? Like every time you switch, doesn't that introduce charge, or it's not significant?
No, it's really not significant. So we are going to publish that very soon, but essentially the contribution from that is completely negligible compared to other sources of background. So what we've done, for example, to measure this is we've read the same pixel millions and millions of times and see whenever we have a jump in the amount of charge that we measured. So that essentially provides us a rate of what's the probability of promoting or creating charge by doing shift in the readout stage. So we are able to measure this very accurately, but our current measurements is that the rate of that is about 1 order of magnitude lower than other contributions that cannot be reduced.
Okay, thank you. Nice talk.
Yeah, thank you.
Nigel, you're next.
Hi, Xavier. A question about that Cherenkov radiation.
Yes.
Idea that you're having. Doesn't that introduce a non-linearity within the pixel? Even if it's, I mean, if you're looking at high charge around a certain pixel that you think is due to Cherenkov, presumably from, you know, whatever's interacting, wouldn't that also add to a noise that you see within that pixel?
So, I mean, that would definitely introduce fluctuations in the amount of charge. So one thing is that we are always running these sensors in a regime in which we are electron counting. So we are particle counting how many we have. So fluctuations are always, we are talking about one electron being there or not being there. So these are physical fluctuations in which you can have some of the charge that would otherwise be in one pixel move to another pixel because they are deposited there by a low energy photon that can travel further and deposit the charge in a different region of the CCD. So in that sense, we are focusing on the low energy region. So for the events that can produce Cherenkov light, we are not really worried about the fluctuations that will be introduced because we are not really looking at those events. And the events that have low energy, the probability of producing Cherenkov light is extremely small. So most of the problem with the Cherenkov light is that high energy events can produce, can be a source of low energy events or single electron events very far away from where they are produced. So that is a new source of background but that we expect that it will be greatly reduced by improving the shielding once we have our system running at SNOLAB. I don't know if that answered.
No, it's good, cool, thank you.
Jeter, you have your hands up.
So I wanted to follow up with that just to understand a little bit more of what do you think is emitting the Cherenkov radiation in response to which charged particles?
So our current understanding is that the Cherenkov is produced by, well, muons, but also by high energy electrons, the ones that, sorry, I'm going to go back.
So like a bismuth electron as well or something.
Yeah, so these high energy electrons that are produced after a Compton interaction with a high energy gamma most of the time, those can produce Cherenkov radiation while they deaccelerate and they hit our particles. But also muons. Those are the particles that we identified as the main source of Cherenkov radiation. Of course, muons will not be a problem at SNOLAB at all. We just need to worry about the environmental radiation, the environmental gammas.
What's the distance scale in that plot? I think it was in pixels.
Oh, each pixel is 15 microns. So overall, this can be a centimeter or less.
Oh, I meant of the shrink of radiation in that plot where you were showing it as
okay, so
on slide 20.
This is related to what we call the halo. So in principle, what we have is that most of the photons that are produced by Cherenkov radiation will be absorbed before 40 pixels. But then you will also have a diffuse contribution of photons that are able to bounce around and travel a long distance before being absorbed. And in here, the halo of 40 would be something like this on this scale. Okay.
Thank you.
Are there any other questions, comments? I have a very naive question. Why the skipper CCD are called skipper? I mean, I think you can still skip the pixel in the other CCD. I don't
actually,
know.
It's a very, very misleading name. It's there for historical reasons. At the time when this was first proposed, the idea was that you didn't need to do the multiple sampling thing for all the pixels. You could do it for some of them and then skip others that you were not interested in. But the truth is that you can skip pixels in a standard CCD too. So that's not a difference. But for historical reasons, that's the name. Yeah.
Oh, okay. Thanks. Are there any other questions? Last call. If not, I would like to thank Javier again. Thank you very much.
Thanks for the invitation.
And hope to have progress soon underground, if so we can see what you will tell us about.
Yeah. I mean, we expect that we will have early science from the system running as SNOLAB very quickly once we are able to achieve the performance that we think we can get. So it's very exciting.
Okay. So thank you very much and talk to you next Monday. Bye. Bye-bye.
Bye-bye.
Congratulations as well, Javier.
Thank you.
Look forward to seeing you here. Cheers. Oh.